Welcome back, everyone. We hope you had a refreshing break and are now ready to engage in the upcoming technical session, which promises to be both insightful and enriching. Let us all remain engaged and open to the new ideas and insights that will surely make this faculty development program a truly enriching experience. We are now ready to dive into the core of today's afternoon session, and we could not be more excited about the learning that awaits us. With that, I would like to invite our esteemed speaker, Dr. Debanjan Konar sir, who will enlighten us with his knowledge and expertise. Now, a very brief introduction about our speaker. Dr. Debanjan Konar sir completed his PhD from Indian Institute of Technology, Delhi, India. Currently, Dr. Konar sir is working as a senior chief engineer and head of quantum computing at Samsung Research and Development Institute, Bangalore. Before joining Samsung Research, he was a Fulbright Nehru postdoctoral fellow in quantum computer science at Purdue University, USA. Prior to that, he was a postdoctoral research scientist at ICTEA, Germany. He also worked as a lead research scientist in quantum computing at Boston QPSI Private Limited, Bangalore. He was a Helmholtz Visiting Fellow in Quantum Computing at Germany. His research interests include quantum computing, quantum machine learning, quantum-inspired generative AI, quantum-inspired optimization algorithms, hybrid classical quantum algorithms, etc. Dr. Konar sir has authored articles in top-notch AI and quantum journals and conferences. We are truly privileged to have Dr. Debanjan Konar sir with us today. Without further delay, I request Dr. Debanjan Konar sir to begin today's session.
Thank you. Thank you for the nice introduction and good afternoon to everyone. So, can I share my slide? Okay, so just let me check. Now it's fine. It's coming full screen.
It is coming in full screen, sir.
Okay, thank you. Okay, so good afternoon to everyone and happy new year to all. So today I will briefly touch upon the a new emerging computing, that is quantum computing. So which I have been working on this field since last 9 years, starting from my PhD. So I will uh, talk about the introductory part of quantum computing along with my research, which I have been doing since last 9 years, and I will enlighten some of the introductory concept on quantum computing. So this is today's content. So I will talk about qubits, superposition, and quantum logic gates, and then I will uh, touch upon the multiple qubits and entanglement. So these are very basics of quantum computing, and then I'll gradually move towards uh, some of your machine learning tools along with the quantum computing, that is called quantum machine learning. So that is quantum support vector machines, then also variational quantum linear solver, and then I'll gradually also move towards uh, my research, which I have done mostly in Purdue University, as well as in Helmholtz Laboratory in Germany. So then I also talk about very interesting topics that I'm also currently working with, one of the quantum inspired tools, that is tensor networks. And uh, then I also talk about there is another new emerging field that is I am already doing with Lancaster University, UK, that is quantum biometrics. So that is a new field for facial recognition. And finally, I will try to touch upon on quantum regression. So I will touch mostly on quantum AI side, though I'll be skipping many things like quantum inspired optimization algorithms. Uh, then we have a quantum search algorithms, which I'm also I worked on this area. Uh, yeah, so I think that would suffice for this 2 hours lecture. So let us first understand what is quantum computing. I think you might heard this definition several times in media, in news. Okay, so so quantum computing is basically uses two important phenomena. One is the superposition, another one is the entanglement. So in addition, there is another type of quantum phenomena that is called inference. So that is very crucial, though we do not explicitly cite this inference term, but that is also very important. Our motivation behind the today's quantum computing. Uh, However, we are basically uh, uses two types of quantum computer. One is the gate-based quantum computing. So most of my work are based on this gate-based quantum computing, where you will have set of uh, gate operations. Like in this circuit, you can see there are three types of gates are are basically applied. One is your Hadamard gate, that is H gate. So Hadamard gate is basically responsible for superposition principle, and there is a rotation gate. So the role of rotation gate uh, is two types. One is the initial rotation gate are used to encode the classical data to quantum data. I'll talk about more detail. I just introducing these gates. So initially, all the data are classical. So as of now, there is no quantum data. Okay. So we need to convert or transform the classical data to quantum data to feed or to input in a quantum circuit. So that is done by rotation gate. Okay. So there are other type ways of doing or encoding the classical data into quantum data, like superposition encoding. Then I said angle encoding. Okay. So these are very popular techniques for transforming classical data into quantum data. So initial level, so as you can see, there are 4 qubits we are using: Q0, Q1, Q2, Q3. So these are input qubits. And initially we have on the first qubit Q0 we applied Hadamard gate, and below that we have applied rotation gates. So initial rotation gates are only used to encode the data through an angle encoding. Okay. In my case, I mostly apply for angle encoding. I'll also explain how angle encoding works. Then you can see there are two bubbles or circle on with the blue line. So this is called uh, control gate. So this is called uh, two-way control gate. There are two control bits. Okay. There's a simplified version of that also. So that is a single control bit control gate. So control gate is basically responsible for entanglement. So you know the entanglement means how correlated each other. So when we visualize any qubits or quantum states, it is always in correlated state. Correlated state means it is superimposed of zeros and ones. Okay. Okay, so then you can see series of rotation gates and two-way cnot gates are applied. So these rotation gates are basically used for updating any qubit informations. And finally, there is another Hadamard gate we used. So this is called gate-based quantum computing. So there is another type of quantum computing that is called annealing based. So annealing based quantum computing is you have might heard about simulated annealing. So there we use a quantum tunneling effect. So tunneling effect is an abstract concept. So all of you are aware of the local minima problem or Bannon-Plateau's problem. So so any optimization problem suffers from Bannon-Plateau's problem. Okay. So to avoid it, so there are various way we have already seen many various classical meta heuristic are applied to get rid of these Bannon-Plateau's problems. But quantum computing has a very interesting feature which can get away of this local trap or Bannon-Plateau's problem. So that is called quantum tunneling. So quantum tunneling is a not a physical concept, is a abstract concept. The reason behind it because we are using quantum tunneling. So what is quantum tunneling? So using quantum superposition principle, I can represent a solution in different location of this valley you can see. So if I represent a single solution in different at a time in different ways, so then these characteristics called superposition characteristics. With the help of this characteristic, I have more options to avoid the local minima. So in it might be also it can also represent a global minima out of all these solutions which are represented simultaneously. So this effect is called quantum tunneling. So I can easily avoid these local minima through various solution at a time. Okay. So this based on this idea, you might also heard about a very Canadian popular company DOF. They have developed a quantum annealer. So this quantum annealer is basically used for any optimization type of problem, or you might have heard about QO problem. So that is quadratic binary optimization problem, and they develop up to uh, 2000 qubits. I used okay in annealer. So all the nodes are actually qubits, but this is not actual quantum computing because all these operations are not quantum. So we are using quantum bits to represent the solution space so that we can avoid this local minima problem or getting better optimization results. So, but these optimization tool are more advanced than gate-based approaches uh, because it has more qubit access and it doesn't suffer from any kinds of noises which we encounter in gate-based quantum computing, like gate noise. Then then we have measure noise due to measurement. There is a very interesting or very important property in quantum computing is measurement. Unless you measure, you cannot visualize these quantum bits or qubits. In addition, so noise also incorporated when we convert or encode the classical data to quantum data in quantum circuit. I'm talking about the left hand side figure. So, but on the other hand, so or on contrary, in simulated annealing or quantum tunneling approach, so there is no such quantum operations. These are all classical operation on these qubits, okay, superimposed qubits. So that is the reason the right side approach is called quantum inspired approach, not actual quantum. So mainly these are two types of quantum computing. Okay, so as a gate-based quantum computing and quantum annealing. So now let us understand what is this qubits and what is basis states. So I prepared this slide when I was in USA, so I used their coin. So this just forgive me, I am not using any Indian coin, so I just use the same figure. I didn't have opportunity to change the figure. Okay, so in classical computing, we use all of you know there is a in binary logic. So our classical computer is basically uh, binary is based on binary systems. So that is 0 and 1, and head or tail, and that is and happy and sad, or you can say switch on or off. So these are all binary states. Now we will, if we use some defined notation, then these are called basis states for quantum computing, and this notation is called bracket notation. So there are, one is the ket, so the perpendicular line is the ket, and there is another brass symbol. So this is called bracket notation. Okay, so this is a special notation. Okay, used by this is the proposed by the scientist. Okay, so uh, uh, so there is no basic difference between the classical computing basis and quantum computing basis. Both are similar types of basis, but it has defined representation. But this representation has some meaning. Okay, so so what is the meaning? Now if we, let's say, if we spin a coin, then it will be mixture of head and tail. So sometimes it will head and tail. So I'm representing the spinning coin using this bracket notation, and which is combination of head and tail with some coefficient or with some probability of head and some probability of tail. So that is alpha is the uh, alpha square is the probability for occurrence of head, and beta square is uh, actually not square, is the norm of alpha square, or norm of beta square is basically occurrence of tail in the spinning coin. Or in other words, we can say uh, that if it is a quantum state, that is a superposition of of 0 and 1. So if we consider alpha head as uh, 0 and beta tail as 1, then it is superposition of 0 and 1 with some coefficient, that is alpha and beta. And I have already stated the alpha square plus beta square must be uh, sum of the square should be unity. Okay, that is a constant. Now these are all we are telling in terms of theoretical concept. Now when we're going to implement a qubit, so how do you represent a basis states? So if you represent a basis state 0 or 1 with the bracket notation, so this notation is called direct notation. So this is a quantum physicist direct, or direct, whatever you can say, direct first proposed this notation. So 0 is basically represented as a column vector 1 0, and similarly 1 is also represent, one basis is basically represented as 0 1, and this is the very easiest way of memorize it. So how do we memorize? So in case of 0 basis, the 0th position will be 1 and first position will be 0. In case of 1 basis, the 0th position is 0 and first position is 1. So this is the way I remember. So so that we are not getting confused, because usually for 0 basis we use 0 1, but in this case not. So you have to understand by the index. So if 0th index is 1, this is 0 basis. If first index is 1, then it is a 1 basis. So as I already, so a qubit or quantum state, that is psi, is a superposition of zeros and 1, and that is with some coefficient alpha and beta. So I can represent this also in terms of column vector alpha beta, and it also represents the same quantum state. Okay, so I can rewrite it in this way: alpha 1 0 plus beta 1. So alpha 1 0 is nothing but 0 basis, and beta sorry, so I did a mistake here. It should be 1 0 and it should be 0 1. So beta 0 1. uh, so this should be 1 basis. Now let us take an example for qubits. So so qubits 1 by root 2 1 by root 2. So these are alpha and beta. So if we square them and take the sum, it should be 1. Okay. So when we are defining a qubit in terms of column vector, you have to ensure that the sum of the squares should be unity. So similarly, for second case, 1 by root 2 and square root 3 by 2. If you square it and sum it, it will also give you 1, and so on. Okay. So now there is a very useful quantum computing tool to implement any quantum circuit. Okay, so you use QSkit, so that is provided by IBM Quantum Simulator, as well as also it is the emulator or quantum hardware is also there. Okay, we'll talk about. We'll show you in the later on. So using a quantum states, a Q. So Q is not initialized with anything, either 0 or 1. So you are considering it is already in a quantum state, and this is called state vector simulation. So there are different types of simulations available in IBM quantum libraries. So you can go for state vector simulation, gate based simulations. Okay. So if so psi is in quantum state, so zeros and one. So we do not know exactly what is the actual state it is. Now we are trying to measure uh, in terms of zero. So if we measure it as zero, then the qubit is zero. But we can also measure in terms of one as well. So it will give you the probability of occurrence of zero and one. Okay. So there is a technique to measure it. So it is a circuit level simulation, but in mathematically there is some jet gate which basically helps us to measure the qubit. Okay. So the quantum measurement is used to visualize the qubit in classical systems. So now we have a two Q basis. So one is the 0, 0. So we can represent this 0, 0 basis within bracket using a tensor product. So that is also called that is a cross product. So here 0, 0 means, so 0 basis is 1, 0. So 0th position is 1, then is 0, and second is also 1, 0. So if you do a tensor product, you can represent two qubit systems. Similarly, for three qubit systems, for 0, 1, 0, then tensor product 0, for 1, 0, 1, and again for 0 basis 1, 0. So I think that will really help you to understand, to remember. Again, for 0 basis, the first position is 1. For 1 basis, the first position is 1. So this way you can easily uh, remember this basis. Okay. So you have n number of bits, qubits, so you can represent in terms of tensor product. So when we'll write as 0, 0 or 0, 1, 0, you'll have to assume that the separate qubits are tensor product. Okay. Form. So if you have a n qubits, so you'll have total 2 to the power n number of defined states, because as you can see from the above, the 0, 0 dot dot 1, there if you have a n number of qubits, so either it can be 1 or it can be 0. So each and every bits can have two possibilities. So therefore there are 2 to the power n number of possibilities, and that is the power of quantum computing or quantum superposition. So in classical bit, they are completely separable 0 and 1, but in qubit, if we represent in terms of block sphere, so that is the imaginary plane or imaginary dimension where we can visualize a qubit. So this is nothing but a superposition of zeros and ones, and uh, in order to separate them, we need to collapse the quantum bits to classical systems. That is called quantum measurement. Now, superposition of basic states of multiple qubits. So, uh, let us consider a quantum system or of a multiple qubits. So, if you have a n number of qubits you are used bits, so that is starting from 0, 0 to 0, 1 to all bits are 1, 1, 1. So we need total cap n number of coefficients to store these quantum systems. Now there is a big question. So this is also called a quantum superposition effect. So I can represent multiple qubits in a single quantum systems. Now for an example, n equals to 300. So there will have 2 to the power 300 number of different uh, combinations, or the total number of coefficients you require, that is alpha cap n. So cap n is 2 to the power small n. So that is 2 to the power 300. So 2 to the power 300 is approximately 10 to the power 90 complex coefficient you require. Now, question is, can we store this number? So, let me uh, rephrase the question. Suppose we want to build a quantum system with 300 qubits. Now, to build a system of 300 qubits, we must have a memory capacity of 10 to the power 90. But let's say this is in terms of 10 to the power 90 bytes. For each qubit, we are considering, let's say, 1 byte. Okay. So 10 to the power 90. So can you imagine 10 to the power 90 number? So total atoms in this universe is less than 10 to the power 82. So then total storage in this world is less than 10 to the power 21. So there is no way we can have a quantum system with 300 qubits. We can go up to, let's say, 50 qubits, because we don't have that memory capacity to store. That is the total storage in the world. That is 10 to the power 21 bytes only. Okay. So that is the one of the challenge in today's quantum computing, though it has a phenomenal theoretical advantage, but we are not making it to practical. Okay. So unless and until we have this huge computing or memory setup. So the same phenomena came, I heard from many experts, in 1980s, when artificial intelligence was theoretically much explored, but there is no high performance computing setup or memory setup to enable them. And then our late 90s started working on it. Okay. There's no computing system that time. So the same similar kind of situation in quantum computing are right now. Okay. So yeah, so we talked about the superposition principle of quantum computing and how powerful it can be. So using this n qubit, we can represent 2 to the power n number of. So 2 to the power n is a exponential time. Okay. So that is huge advantage we can get in terms of superposition. And if I give an example, uh, like you have all of you know about genetic algorithm. So when you represent the initial population uh, using a chromosome, okay, so I can represent various solution. Let's say if you use 3 bits chromosome, I can use 3 bits qubits to represent 8 different solutions at a time. So that is called superposition principle. Whereas in classical genetic algorithm, I need 8 uh, uh, 8 different chromosomes to store them. Okay, but in a 3 bits qubits, a 3 qubits chromosome, I can represent all different solutions in a single solution or single chromosome. Okay. So, okay, so there's another property that is called quantum measurement. Unless we do not measure it, we cannot visualize the quantum states. Okay, so once it interacts with this classical environment, it collapses, or it is called quantum measurement. Now, so in mathematically, so to measure a quantum state x, so x is a basic states in a quantum state psi. We use this formula, probability of x is nothing but, so when we measure, we measure in terms of probability. So that is the inner product of x out of psi, and we make its perfect square. So we use this analogy to make you better understand what do you mean by this quantum measurement. So when we define a quantum state or qubits, we use this spinning coin concept. So a quantum state is nothing like a spinning coin. So if we touch the spinning coin, either it will stop after some time to head or tail. So this head and tail are nothing but basic states. So in mathematics all same. So if you have a spinning coin psi, that is combination of alpha 0 and 1 basis with coefficient alpha and beta. If we measure them, so either it will give you some probability alpha square and beta square for the occurrence of 0 and 1. So that is the beauty of that. I can see the same information as 0 and 1 simultaneously. Okay, with with some probability. They may be equal, they may be different. So these are theoretical idea as well as these are analogy we use. But when we how do we in programming? So we use a jet gate based measurement. I'll come to that part. Jet gate. What is jet gate? So jet gate measurement is very popular gate based measurement techniques. So we apply jet to jet gate operations successively to measure any qubits. Okay. So this is also called zero. So because jet gate is basically it ranges from 0 to 1. So it basically if you apply jet gate on 0, it becomes 1. If you apply jet gate on 1, it simply remains 1 and it is simply splits. Okay. So that basically ensures the amplitude remains same. The only thing it changes its phases. So that is the reason jet gate is very useful in quantum measurement. Though there are different types of measurements are there. So let us take an example. Suppose we are trying to measure 0 in the given quantum state psi, 1 by root 2 0 plus j 1 by root 2 is 1. So this is the complex states. Okay. So the imaginary number j is there. So in order to to measure 0 basis out of this psi, we do this is called inner product. So I am using some special kind of notation. This notation is read as bra 0 ket psi. Okay, this is the convention we use. So then again another bra symbol. So we are trying to find out 0 out of psi. Okay, what is the probability of that? So the simple is we just operating 0 on each and every basis, and you can easily answer. So if you look at very closely, so 1 by root 2 0 inner product 0. So basically we are trying to extract 0 out of 0. You will definitely get 0 always. Okay. So that is the reason it will give you 1. And the next part you are trying to find out 0 out of 1. So inner product, this is this symbol like bra 0, ket 1, then bra. So this symbol also signifies the overlap between 0 and 1. Okay. So there's no overlap. So that is the reason the second term comes out as 0. And after a calculation, it comes at 1 by root 2. So the probability for finding 0 out of psi is nothing but square of that. So 1 by root 2 make it square. So it is half. Okay. Similarly, if you try to find for 1, you can also get 1 in this case because it is equally superimposed states. So alpha and beta both are same. Now you might ask then what is the role of J? So as far as the amplitude is concerned, this J or this is called phase. Okay, so this phase doesn't make any impact, but definitely it will impact in terms of or direction or phase. Okay, so that is for local measurement that you can avoid. Okay. Okay, so general state of qubits, as I said, that is where C alpha beta belongs to C is a complex number. Okay, so how we visualize it, this is an imaginary plane or sphere. So in this case, the qubit is on the x-axis. So this is called plus state. I am coming to that plus state. What is plus state? This is also called equal superposition states. That if you whatever example we have taken, psi equals to 1 by root 2 0 1 by, these also called equal superposition states. Okay, so here we have introduced some parameters. So that is e to the power I theta. So this theta is basically the angle it makes with the positive direction of x-axis, y-axis, or z-axis. So based on that, this theta or phase is basically decided. Okay, so for our simplicity, we often ignore this term e to the power I theta in qubits, but in general, it is always this form. Okay, so like we always consider the qubit is on the sphere for our better representation or simplicity in the calculation or computations. But in reality, the qubit is not always on the sphere. It is maybe inside the sphere. So that is called radius. So if radius equals to 1, then it will be on the sphere. Okay. So yeah, so that will come when we talk about rotation gate. So this is the various ways of representing a qubit. You can also represent in terms of cos and sine component. Okay, so these are in polar coordinate representation that you all of you understand in trigonometry. Okay. So these are the two concepts we are talking about. One is your superposition. Another one is uh, measurement, quantum measurement. Okay. Though we have not talked about another very important property of quantum computing, entanglement. So that I will come when we talk about the measurements, quantum entanglement. Sorry. Okay. Now we will be moving towards quantum gates and operation on qubits. Okay. So Uh, so initial 1 hour I will talk about this basics so that you can understand the remaining part, which is more towards research or advanced topics, okay, on quantum machine learning or quantum AI. So X gate. So X gate is nothing but a inverter gate. That is all, if you know, in classical computing. It's simply, so here it is a Pauli X matrix we use. Pauli is the kind who first proposed this matrix representation for any gate operation, because here qubits is two-dimensional information. In classical bit is a single dimensional information. Okay, so this is a X gate, okay, or it is also inverter gate. So the matrix is very simple: 0, 1, 1, 0. If we apply X gate on any qubit, it will simply invert. If we apply on 0, it will become 1. Just do the matrix calculation, matrix multiplication. So X is your 0, 1, 1, 0, and 0 is a zero basis. You remember the zeroth position is 1, first position is 0. So if you do that, then you will get 0, 1 basis. So 0, 1 basis means first position 1 means 1 basis. Okay. So just you flipping the, similarly, if you apply on x1, you'll get 0 basis back. So initially, from this diagram, from this block sphere diagram, you are at 0 basis, okay, or 0 state. You can, whatever you can say. So that the arrow is currently showing. Now, if you perform X gate, it simply goes to the south pole, from north pole to south pole. Okay. So in block sphere, the north pole is 0 basis, south pole is the 1 basis, and remaining combination of 0 and 1. Okay. So there is another gate operation that is called Hadamard gate. I have already introduced this gate, H gate. So this gate is basically mainly responsible for creating superposition in any qubit. So initially all the qubits are in reset state. Okay. Usually it's not necessary. You can also start from 1 basis also, initializing the qubit on 1 basis. But we always start from reset state, like any gate operation in classical computing. Okay. So Hadamard gate is a very interesting gate. So it is designed uh, by the scientist Hadamard. So 1 by root 2, 1, 1 minus 1. So this gate is designed in such a way so that you can give a equal superposition to this without any bias. Okay, to a qubit state. So let us see how it works. So we are applying Hadamard gate on 0 basis. So we just we am writing Hadamard gate as 1 by root 2, 1, 1, 1 minus 1, and 0 basis as, you know, the 0th position is 1 and first position is 0. So if you do the matrix multiplication, then you will get. So here I have just made a step jump. So if you do the matrix multiplication and if you rearrange it, then you will get in this position. Okay. So in the slide, I have less space. Okay, so sorry, so there are a lot of noise outside. So here I have represented as 1 0 column vector and 0 1 column vector, and these are nothing but 0 and 1 basis. So as you can see, if we apply Hadamard gate on 0, 0 means reset state, reset qubit. Then we are reaching 1 by root 2, 0, and 1 by root 2, 1. So this is called equal superposition, because alpha is 1 by root 2 and beta is also 1 by root 2. And if you make a perfect square, then it has become half. So the probability of occurrence of 0 in this qubit is half, and also probability for occurrence of 1 is also half. Okay, so that is reason it's called equal superposition. Okay, so you are at initially it is reset state means zero state, north pole. Now if you apply Hadamard gate, it will simply move to equal superposition gate or towards x-axis, and this is also called plus state. So when I say plus state, that means you have to visualize the qubit on the x-axis, positive direction of x-axis. Now similarly, if you apply, yes, so Hadamard gate on 0, it is represented as a plus state, if or positive state. If we apply negative, or if we apply Hadamard gate on 1, so it will give you a minus states. Okay, similarly, if you can do the calculation similarly as 0 matrix multiplication, so in case it is 1 0, the column vector will be 0 1. This is because this is a 1 basis, so it will come out as 1 by root 2 0 minus 1. So see, there is no difference in terms of amplitude, they are all same, but in terms of phase, the one basis is a negative phase. Okay, so that is the difference. Okay, so this is called minus state. Okay, this is also equals superposition, but it's a with minus phase. But there is a significance of this when we treat as a qubits, but when you measure it, it doesn't have any impact because local measurement doesn't have impact on the phase. So I have tried to summarize this X and H gate for all types of operation. So if you start from a left hand side X gate, so I have represented all the qubit in terms of column vector. So you'll have to assume these the values of this column vector are nothing but alpha and beta. These are coefficients. Okay. So if we apply, you can easily do this on your own. So if we apply 0 1 and X gate, it will become 0 1 means one state, one basis. And if you apply X gate or inverter gate, it will become just it will complement each other. So 0 becomes 1 1. So it becomes 1 0. Okay, 1 0 means it is 0 state. So it was 1. Similarly, there is a same loop of red color. So 1 by root 2, 1 by root 2. Even if you just complement them, it remains same. So this is called equal superposition state. So in other words, if you apply X gate on plus state, then it remains plus state. And minus 1 by root 2 plus 1 by root 2 is also, see, it's just changed. Minus becomes plus, plus becomes minus. So this is also minus 1 by root 2 and plus 1 by root 2. So minus 1 by root 2 means it is negative phase as 0 basis. Okay. And in this case, it is a negative phase at the 1 basis. Similarly, you can just generate anything. So similarly, from Hadamard gate, if you can visualize from 0 1 to, so 1 0, 1 0 is nothing but 0 basis. So if you apply Hadamard gate using this yellow colors arrow, you will get a plus state or equal superposition state, that is 1 by root 2, 1 by root 2. Okay. Now I have taken an example to understand better. So initially, my state is a 0 1. So 0 1 means it is 1 basis because first position is 1. Then we apply, so initially at 0 1. So now we applied a X gate. X gate is basically inverter gate. So if we apply inverter gate, 0 1 becomes, you can follow the left hand circle behind so beside the circuit. So 0 1 will become 1 0 after getting first X gate, that is marked in red. Then from 1 0 you are applying Hadamard gate. So you can just refer the above figure to get, if we apply one Hadamard gate on 1 0 column vector, it will give you 1 by root 2, 1 by root 2. So at this state, then again you are applying another X gate, third X gate, sorry, third gate, that is X gate. So if we apply X gate, it remains 1 by root 2, 1 by root 2. Now you are 1 by root 2, 1 by root 2 after first 3 gate operation. Then is the second Hadamard gate. So if you have again, if you apply Hadamard gate from 1 by root 2, 1 by root 2, you will get back to 1 1 0. Okay. And Finally, the last one is X gate. So again, if from 1 0, if you apply the X gate, you will back to 0 1 again. So whatever input you are given, that's you are getting the same output after this series of XH XH X operation. So what is this operation? Can anyone tell me? What is this gate actually? Yeah. So anyone else? No, right? Yeah. Okay. So this is called a buffer gate. So we use as a buffer gate in quantum computing. So whatever input you are giving, thus you are getting same output after some temporary time. Okay. So okay. So now we'll move to another kind of gate operation, that is jet gate. So jet gate is basically is also, yes. Is there any question?
Right now?
Yes, yes, you can, sure.
Sir,
Anytime you can.
sir, one question is posted in the comment box. You can see
Okay,
also.
so I'll just
Uh,
using full screen. So let me check.
Dr. Mohanandipal asked, how does quantum speed up as compared with classical be measured in real QPU?
Uh, okay, I think yes. So whatever now I'm in the discussion stage. So these questions looks very like I'll go to that part. Okay, anyway, let me uh, answer your question. So uh, okay, so there in quantum computing, so speed up is coming from specifically this superposition principle. Okay, because quantum entanglement is very computationally expensive operations. So uh, I can represent the multiple information using a single qubit. Okay, though I am showing using a 0 and 1 bi-level system, but in reality, if you look at the quantum mechanics, the actual information is not binary. Is a it is a mm, uh, multiple information. It can be any number of operations. That is called qubit. Okay, so but since our systems still are binary systems, so we mainly rely on this binary abstraction. So due to that, we are also incurring many errors, okay, into the systems. uh, I have also worked with up to qtreat, like 3 level systems, quantum systems, and recently University of Waterloo also made a device based on qtreat. So if you increase the number of levels, your approximation also increases, as well as you can you can represent multiple information using a single qubit. And that and in addition to that, you are also uh, encouraging the quantum superposition principles. So that basically helps you to search as number. Let's say if I are doing a search, so if you can represent the multiple solutions at a time, so you can use parallel kind of search. Okay, so these are inherent characteristic without deploying any parallel device on it, like in classical we do parallel component on that, which is it has the inherent characteristic of that. So this is the mainly the superposition gives us this advantage. Okay, but yes, so as you asked the QPU, so as of now there is no quantum advantage observed. Okay, so that is mainly due to the computational power, or you do not have that kind of hardware which can basically give us real quantum advantage at this point in terms of speed. Okay, so as of now, we run our quantum circuit in Bayesian quantum circuit. So in standard GPU systems. So, but that is very slow. Even it's slower than standard other classical models. Okay. Uh, but there is also another NVIDIA is already coming up with you might CUDA quantum. So there is an accelerator on top of a GPU. So this is a tensor network based accelerator, okay, an optimizer you can say. So that is getting accelerated, but there's not still it's slower than a classical computing. Okay. So in one line, if I answer your question, so in today's till today, the quantum computer is slower than classical computer. Okay. But theoretically, many algorithms are basically showing quantum advantage, like robot search algorithm. Okay, so you might know about robot search. So this is gives a quantum advantage theoretically, not practically. Demonstration is not possible yet. Yes.
Thank you, sir.
Yeah. Okay. So shall I continue, or do you have any other questions from other side?
Right now, sir, we do not have any more questions, so you can please continue.
Yeah. So I will take more questions at the when I reach my some of the use cases I will show you. Okay, on more application side. Yeah.
Okay, sir.
Okay. So yeah. So as I started with the JADE gate. So JADE gate is similar to X gate or or inverter gate, but with some phase difference. That is, it has minus symbol. Okay, but even if it is X gate was the leading diagonal element was 0 0, and the other diagonal was 1 1. But that is the main difference. But structure wise it looks similar. It is also similar symmetric kind of gate. So there is another way of noting representing the JADE gate. Okay. Okay, so how it works? So if we apply JADE gate on 0 basis, it remains 0. So it will not disturb the 0. Okay, but if we apply on 1, it will just keep at 1 but with negative phase. So that is very simple. So if you are at the north pole, if your qubit at the north pole, that is 0 basis, it remains as 0 after applying around JADE gate. But if you are at the uh, here actually I have shown some different examples, but don't correlate with 0 and 1. So if you are at the 1, positive 1, that I have not shown here, then it will be the other direction of. So here the other direction is not actually, because it is a sphere, so don't consider the other direction is the opposite direction of 1. Okay, so it is not always so, but it's the same direction with the negative phase. Okay, but I can show you from with the y-axis, that will be easier for you to understand. So if it is a positive y, it will be simply the other side of y, the negative direction of y. Okay, so direction will be different. Okay. So there is another gate, that is U gate, or in simple terms we also call unitary gate. So unitary, in a sense, we can recover these gates. Okay, so recover the information. So if you give some input, you apply some gate operation, and if you get the output, from the output itself, I can recover the input. That is the beauty of quantum gates. This is called unitary gate. Okay, so a quantum state, let's say psi, is represented. It is not actually on the sphere. So we have generalized it. We have taken us inside the sphere, and we can represent these quantum states in terms of theta, phi, and lambda. Okay. So theta, phi. So theta is basically the angle it makes with the positive j directions. Okay. And phi is basically its angle it makes with the x-axis with its projections, and lambda is basically taken as the radius of this amplitude of or radius or amplitude of this qubit. Okay, so these three parameters we set to represent any qubit in this pair. So there are infinite number of combination can possible in a 3D sphere. So I can do various types of rotation about x-axis, about y-axis, as well as about z-axis. Okay. So let us simplify it more. Okay. So if we set lambda equals to pi by 2, okay, and phi equals to minus pi by 2, in this u omega phi and lambda, we'll get this. So this gate is called rotation about x-axis. So that is cos omega by 2 minus I. So all of you, I think, are familiar with this type of gate. This is called rotation gate. Okay. So if we set lambda phi equals to 0, it becomes RY gate. So this rotation gate about Y is free from any any complex term or imaginary term, you can say. So this gate is used. I prefer these gates to encode the classical data to quantum data. And if you say lambda equals to pi by 2 and phi equals to minus pi by 2, then you will get rotation about z axis. So these also not free from any complex terms, but these terms you can easily use in quantum circuit. Okay. So the role of the rotation gate is, as I already introduced, the rotation gate. The initial rotation gate are used for encoding classical data to quantum data. Okay, and the later on, whatever rotation gate are used, these are mainly used to update any qubit. Okay, so let us take another quantum state, that is, you can see 1 by root 2. So this is minus 0 1 1 0 1 1. So when I'm writing 0 0, so you'll have to understand there are two bases, 0 and 0 are tensor product. Okay, so we represent in this way. So that is the most convenient way of writing quantum states. So, but I can factorize this 2 qubit system into 2 spins. So spin is nothing but 2 qubits. Okay, so I can factorize in terms of 1 by root 2 uh, 0 0 plus plus 1. Just you do a matrix uh, multiplication, you'll get these results. Okay, so you can see I can easily factorize these two in terms of two different quantum systems or qubits. So that is the reason it's called untangle. Untangle means you can separate them. Okay, but if we take in another state, let's say I represent as phi plus. So this is 1 by root 2 0 0 plus 1 1. Now the question is, can we factorize into two quantum states? So let us try. The answer is no. So I'm giving you the answer first. So let us try whether we can do or not. So first we have simplified it. So 0 0 means the tensor product between the zero basis 0 1 0 1, and 1 1 is 1 0 and 1 0. Okay. Then we have simplified it, and we have tried to factorize in terms of 2 qubit system. AB is the first qubit and CD is the second qubit. So we have now. Now, can you tell me any for any solution for can we solve this problem in to get ABCD? Okay, I have not shown in the slide, so I just skipped it. Uh, uh, so I removed that slide. So there is no possibility to get ABCD from a single solution. Okay, single equation. So therefore, there is no quantum state exist which can factorize this 1 by root 2 0 0 plus 1 1, and that is the reason it's called fully entangled state. Okay, so when I'm saying fully entangled means they're 100% correlated. If you want to separate them, we need to take some defined measurement techniques, so that I will not discuss here. So that is called multi-qubits measurement. Okay, but you cannot separate them. Okay, or you cannot factorize them. So with this, with the help of these states, the quantum communication systems. Okay, you might also heard about uh, quantum cryptography. So that is so when we send some data from some channel, so it might be corrupted. Okay, or it may be exposed to the external world. So how we can encrypt the data? So one of the technique they use, that is a fully entangled state. Okay. So I talked about most of the gates. That is, I think, the last gate, that is cnot gate. So far, whatever gates like Hadamard gate, X gate, or inverter gate, then jet gate, so rotation gate. These are all single qubit gate. So these are all applicable on single qubit. But there are other gate, that is cnot gate. Cnot gate is a 2 qubit gate. So that is the reason this gate is most expensive gate operation in quantum computing. And when we run any variational quantum circuit, due to this gate, it becomes very slow. Okay. So because it has to do for 2 qubits gate, it needs to do 4 matrix multiplication to get the calculation. Okay. So I've used a NAND gate operation. So all of you are aware of the NAND gate operation. So NAND gate operation is, if it is 0 0, it is 1, 0 1 is 1, 1 0 is 1, 1 1 is 0. So if any one of the input is 0, then output is 1. Okay. So that is a conclusion we can make from NAND gate operation. So we use similar kind of operation in called cnot gate. So as you can see from the right hand side figure, the upper one is called control bit, okay, or control qubit, and the lower one is called target qubit. So control qubit will enable the target operation or lower qubit operation. So if the upper qubit is 1, that means it's enabled. So, and what it will do, it will simply invert it. So as you can see, the first combination 0 0, so control qubit is 0, so there is no change in the target qubit. In the second case of 0 1 input, the control qubit is 0, so there is no change in the output, so it remains as 0 1 output. And third case, 1 0 combination, the moment the control qubit becomes 1, the upper one, that is black dot, it will change the target qubit from 0 to 1. So therefore, output becomes 1 1 or 1 0. And finally, likewise, so the final one is 1 1. This is also enabled. So 1 0. So can anyone tell me what is the interesting observation from this gate operation, which is not present in the classical computing? Okay, so whatever the inputs, we can generate the output, all the input combination. So you can see any inputs we are getting in the as an output. So what is the advantage of it? Suppose you have applied 0 1, sorry, 1 0, you got 1 1. Now you want to recover that input from the output. What will do? I will input 1 1 and I will get the 1 0 back. So that is the main what you can say beauty of this cnot gate operation or 2 qubit unity gate operation, that I can recover the information from the output itself. So that is the reason people are saying that quantum could be a game changer, because suppose if we lose some information, okay, like even image processing, if we lose some image compression, we can recover the data. Like you might also heard about tensor completion. So tensor completion is also the classical representation of quantum information. So I can recover an image even if it is some pixels are missing. Okay, from the output itself, I can recover the input. Okay, so that is the one of the inherent characteristic of cnot gate operation. So this is a cnot gate matrix, is bigger matrix. So if you look, cnot is nothing but X control X gate. Okay, so as you can see, the blue bits are nothing but X gate matrix, if you remember. Okay, and on top of it, in CX gate, it is 2 1 1, diagonal 1 1 is used to basically represent the control bit. Okay, so you can easily see by just doing some calculation with cnot gate. Okay, so now you can ask why it is 2 1 1, because it is a 2 qubit gate. Okay, that is the reason we used 2 leading 1 1 in this matrix. Okay. Oh, sorry, actually I just misplaced this slide. Actually, this slide should be after this. Okay, so yes, so here I was talking about the factorization. So we tried to solve this one. So we got this solution AC, AD, BC, and BD. So there is no way we can solve this problem. So these are unsolved factorization. So we can say that there is a 50% chance of collapsing to 0 0 or 1 1. Okay, so that is also not looks very promising, because how do you know that what in which state is 0 0? Okay. Okay, so we can achieve this fully entangled state, that is 0 0 1 1, using this simple circuit. So if I explain this quantum circuit, this is very simple. So initially, so I have initially both the qubits A and B are reset state. Reset means 0, 0. So I can combinedly write these two qubits as 0A tensor product 0B. So tensor product will not be explicitly mentioned, but you'll have to assume that is 0A, 0B. Then I am giving equal superposition for the A qubits using applying Hadamard gate. So if we apply Hadamard gate from our previous discussion on 0 qubit, it will give you a plus state or equal superposition state, if you remember. Okay, so that is nothing but 0, 1. And this is about the first qubit. And the second qubit still remains 0b because we didn't do anything yet. Okay, so I've written 0b. Now I'm applying a cnot gate operation. So I'm taking the first qubit, that is A, or is also written as MSB here. So A as control and B as target. So as we have already seen that if the control is enabled means 1, then it will change the target, otherwise it remains same. Now we'll have to close very carefully. So now we'll see the first qubit. If the first qubit is 0, there is no change in the B qubit. B is the target, it remains 0. Again, if the first qubit is plus, first qubit is 1, then it will change the second qubit. So what will change? So 1 will becomes 1b. Okay, so the first one is 1 by root 2 0a 1a 0b. Then I just simplified it, so don't see this. Okay, after simplification, you see the last one, that is 1 by root 2 0a after the operation of cnot gate operation. So 0a remains 0b, 1a simply 0b becomes 1b. Okay, so that is flipped. Okay, so so then we are obtaining actually 0, 0 and 1, 1 state from this. Okay, so if you have any question to understand this circuit operation, this is very simple quantum circuit operation. Just we use two gates, one is Hadamard, then followed by a cnot gate operation. You can also ask. Okay, so I think I have taken almost more than 1 hour. So I would like to take 15 minutes break. Okay, so just let me tell you another one. Mm, Okay, okay. So I am just giving you a. You can also do this or take the assignment. That's up to you. So I'm giving a quantum circuit for your assignment. You can also work out in this 15 minutes, or you can take break, whatever you like. Okay. Uh, So these are three qubit operations, so 0, 1, 0. So unlike classical circuit, the quantum circuit varies over time. So time is basically, time axis is along x-axis. So here I have written phi 1, phi 2, phi 3, phi 4 to measure the intermediate outputs for this quantum circuit. So initially I have applied Hadamard gate over tensor product 2, means it is applied, Hadamard gate is applied on both the qubits 0 and 1 above 2 qubits. R90 means we have applied rotation about 90-degree angle. You can consider the RY rotation. And X gate is basically inverter gate. cnot gate is already there, and also we have used Z gate. So you can carry out and you can tell me the answer uh, if you like to do in this 15 minutes. Okay, and then I think I can start with this quantum error correction. Okay. Okay, so this syndrome that I will touch upon on this. Okay, so then I will move to directly some of the use cases of quantum. So as of now, I am just building the foundation or introduction of to quantum computing, and then I will talk about. Okay, in the okay. So if you have any question, you can ask.
Sir, I think one raised hand is there. So, Mr. Sayantan Kaur, are you there?
Yeah.
Mr. Sayantan Kaur, your hand is raised. So, if you have any question, you can ask. Or anybody else, any other participant, if you have any question.
So I hope everyone is back.
Yes, sir.
Okay, so shall I start?
Yes, sir, you can start.
Okay, thank you.
Yes, sir. Yes, sir. Yes, sir.
Okay, so okay, so I made the animation. You can follow the animation. Okay, so how this quantum circuit works? So let me. Uh, so I'm just measuring step by step in the each and every time interval. So at phi 1, I'm representing all these three qubits as a tensor product. So 0, 1, 0. Or you can also write directly within a bracket symbol 0, 1, 0. So I'm applying Hadamard gate on first two qubits, 0 and 1. So let us apply it and we measure at phi 2. So if we apply two Hadamard gate operation on these 0 and 1 qubits separately or basis separately, you will get it. Because that we have already seen. If we apply Hadamard gate on 0 basis, you will get a 0, 1 by root 2 0 plus 1. And if we apply on 1, you will get always 0 minus 1. So you remember this call the first one is called plus state and second one is called minus state. Okay. So we have measured up to phi 2. Then we'll see what is phi 3. But in phi 3, there are two operations simultaneously happening. One is uh, a rotation gate. So that is rotation gate is applying on the first qubit 0 and cnot gate is operation on second and third qubit. So let us simplify it. Then it will be easier for us to uh, do the operations. So I have just simplified. I have bring the zero into the in the bracket notation 0, 0, 0, 1, 0 like that, and finally I got this. Okay, then I will apply rotation gate on the first qubit. First qubit is the leftmost bit. Okay, so if we apply rotation gate, so I have made a phi 3 star because that is a only for rotation gate calculation. So I have applied on phi 2. So I have also underlined the middle qubit because middle qubit is the control qubit. So I have already applied rotation gate, and if we apply rotation gate, 0 becomes 1, second 0 becomes 1, third one becomes 0, and fourth one is there is minus 1, there is becomes plus 0. So now you may ask why I have shown in the next slide. And I have also marked the middle qubit because the middle qubit is the target, sorry, the control qubit for the next operation, that is cnot gate operation. Okay, so in the meantime, I have used rotation about y-axis about 90 degree. 90 degree means pi by 2. So if we apply on 1 0, 1 0 means 0 basis, you will get what? 1. If we apply on so I've just calculated cos pi by 2 minus sin pi by 2, sin pi by 2, cos pi by 2, that comes out as 0 minus 1, 1, 0. So, and if we apply on one basis, you will get minus 0. I just replaced this value in my previous slide. Okay. So what I've seen that if it is 0, it is becomes 1 basis. If it is 1, it comes at minus 0. So just use, we replace this result here. Okay, so I don't know, I have shown it's not here. Yes, so phi 3 comes out as this, and in between in phi 3, I have applied cnot gate. So if the middle qubit is 0, there is no change in the target qubit, that is third qubit, so it remains 0. And since the second qubit is 1, so it will be changed. So 1 1 0 will become 1 1 1. So third one also 0 0 0. So middle qubit is 0 means no change in the third qubit. And last one is 0 1 0. So since middle qubit or your control qubit is 1, that means it is enabled to change the third qubit. So 0 1. So what are the qubits it change? That is second one 1 1 0 will become 1 1 1, and 0 1 0 will become 0 1 1. You see the same thing is reflected in the results. So the second is become 1 1 1, third one becomes 0 1 1 after operations, rotation, and so rotation we have already taken up. So that is the first qubit 1 1 0 1. Okay, So due to this minus 0, this plus becomes, because it was initially minus, if you have noted in copy, then you can see initially it was minus 110 in pi 2. Okay. And finally, so what is the next gate operation? There is, I think, Z gate operation. So I have to go back again to check what is the gate operation. So X gate on the first qubit and Z gate on the third qubit. That is very simple. So I can do, so first qubit X gate means 1 becomes 0, 0 becomes 1. So, and if you apply Z gate, then Z, uh, it will, Z gate is on the third qubit. So Z gate third qubit 0 becomes, 0 remains same. If it is 1, then it is becomes plus. You can see. So if you remember on the Z gate operation, so Z0 0, Z1 minus 1. So, and okay, so finally you'll get these results 1 by 2, 1 0 0 1 minus 0. This is the column matrix. If you simplify it, and you'll get this. Okay. Okay. So you can work out on your own, and you can just, okay. So before that, I just keep another slide, that is quantum error correction. So quantum error correction is itself a big research domain. Most of the quantum theorists, theoretical physicists are working on this, on how they can make a error-free quantum circuit. So just I'm also not an expert on this quantum error correction. So that is different field from my interest. Uh, so here is a syndrome measurement. Okay. Syndrome measurement is basically used for error correction. So this is very simple error correction technique. So you can see that I am using psi 00. So psi, I have not defined what is psi here. So I have defined psi in terms of these 3 qubits. Okay. But I have defined the other 2 qubits, these 2 qubits, which are reset state or initialized with 00, are called auxiliary qubits, and psi is the actual input qubit or input information you are going to transmit. So psi is basically uh, alpha 0 plus beta 1. Okay, it's a combination of 0 and 1, but I certainly know what is the other auxiliary qubit 00. So I can represent these 3 qubits in a single system, that is alpha 000 and beta 100. I have marked the auxiliary qubits. Auxiliary qubits is basically temporary qubits which help us to competitions. Okay, so, or extra qubits. So I have represented the auxiliary qubits in black bits 00, and the input qubits in terms of in violet color. Okay. So now I have applied to cnot gate operation, keeping my input qubit as the enabler or controller, and the corresponding auxiliary qubits are the target. Okay. So if we perform these 2 operation, okay, so how do you do the operation? So if the violet bit is 0, there is no change in the target bit, as I keeping on telling you. Is if the target qubit, sorry, control qubit is the violet, that is psi, is 0, that means it is disabled. There is no power to change the other qubits. Okay, so it remains same. So it is remains same after these 2 qubits I have shown in blue arrow. Okay, but in beta part, if the qubit is 1, because qubit is maybe 0 or 1, I don't know which state it is. So when you are calculating, you'll have to calculate for both 0 and 1 both. Okay, so I am calculating for 0, 0 is done. Now for beta part, qubit is 1. So since it is 1, it is enabled. That means this second dot, black dot, is enabled. So it will certainly change the qubit. Now it apparently looks that it will change on the second qubit. No, sorry, third qubit, that is the second auxiliary qubit. No, it will change both, because whenever you are representing a quantum system, they are tensor product. So their tensor product means they are factorized, but we are combinedly representing alpha 00 plus beta 11. So in this case, since it is violet 1, beta 1, it will change both the 00 to 11, and that happened after applying to first CNOT gate. Now, maybe due to some unforeseen reason, there's some bit flip occurred. So you can do for other bit flip. Let me just explain for first bit flip. So first bit flip happened. So bit flip will happen in the your content, not your auxiliary qubit. So content was 0, alpha 0, beta 1. So after bit flip, so alpha 0 becomes 1 and beta becomes 0. Now you have to recover. How do you recover? Because this is this is happened, but that is not in your knowledge. So in order to recover it, we use, so similar to, if you remember, checksum code, where error correction code in classical communications also. Okay, the so similar type of things are replicated through quantum circuits. Okay, then we applied same gate operation to recover it. Okay, so if we apply same gate operation, I think I need not to explain again. So alpha 1, so 1 means now this 0 to 2 zeros becomes 1 1, and next is beta 0, that means it remains 0 1 1. But that is not the actual result. To get the actual result, you need to do the reverse operation, because after bit flip you are applying these two CNOT gate operation. Okay, and so now you may ask, what is the purpose of the first two CNOT gate? To check that whether the your input is enabling the auxiliary qubits or disabling it. Okay, to check its content only. Okay, and the second CNOT gate is also checking the content after bit flip. But if you check the content will remain same. It will not change. So to change it, because you have already done a bit flip, we have to do the reverse operation. So I am doing a reverse 2 qubit CNOT gate. So here the control bit is 2. So control bit is 2 means if the both the auxiliary bit is 1, then it will change. Otherwise not. Because when I change this, when I applied these two CNOT gate operations, if the both the auxiliary bits are changed, then only your input will change, otherwise not. Okay, so this is the way actually we have built this system. And if you follow the operations, so after bit flip, if you do two CNOT gate operations, so one becomes 1 0 0 becomes 1 1, and beta 0 1 1 becomes 0 1 1, remains 0 1 1. And after this reverse operation, since both are 1 1, alpha 0 1 1, beta 1 1, so both are both has to be enabled, both has to be 1 1, then alpha will change. So alpha will become 1, 1 becomes 0, and beta 0 becomes 1. So that ensures you are getting the same information what you have transmitted. So though your auxiliary qubits are changed, but your main input qubit remains same, alpha 0, beta 1. Okay, so this is the way. Similarly, you can do for second qubit flip. So it will always reserve its content. It's not going to change. So this is a very trivial way uh, of doing it. But for the more complicated circuits, it's not so easy. Okay, so the operations are like surface code and various types of error correction techniques people use. Okay. Okay, so I think that is all about introduction and all this familiarity with the quantum computing. Now I will move towards some of uh, your well-known topics with the quantum. I can say quantum flavor. So like support vector machine, all of you know. So I will just talk about quantum support vector machine with some experimental results, so that you can understand what are the use cases of quantum computing. Okay, so though I have confined myself in this lecture with the machine learning, so that can be there are other works or areas where uh, we are working. Okay. Okay, so if you have any question, you can quickly go ask me. Otherwise, I'll go through very fast, because it is already 4:10, I think. Yeah. Okay. Okay, so quantum support vector machine. So in quantum support vector machine, all of you are aware of the classical support vector machine. So in quantum support vector machine is there is a QPU, that is quantum processing unit. So in quantum support vector machine, the entire part is not quantum. Only the kernel trick or kernel calculation part is quantum, using a quantum circuit or quantum processing unit, and the rest. So once we design the kernel using a quantum circuit, it gives us some probability. So, and although I have defined all equal probability, but through this kernel trick, we generate some probability, and based on the probability, we go for classification through a standard classifier or classical classifier. So here the role of quantum is only to generate the probability. Okay, so I can say it is not a fully quantum support vector machine. In rather, it is called quantum enhanced support vector machine. Okay, uh, so classical SBM is basically act as a classifier in this case based on this probability generated through this quantum circuit. So this quantum circuit has acted as a quantum kernel. Now, what is quantum kernel? So before we go to quantum kernel, let us understand what is classical kernel. So classical kernel, all of you know that there are two feature two feature dimension xi and xj. So we have used some dot product between these two vector to do a kernel trick. So everybody knows this example. So if you have a data set which are not linearly separable, so we can map to higher dimension, that is z direction, x1, x2, x3 direction, and using a classical transformations function that is called a feature map pi x. So that is x1 square x2 square we used, and we can easily separate them by through a plane. Okay, so once we transform these data points to higher dimension. Okay, so I think that is. Now what is the difference in quantum kernel? So as you can see in the classical kernel, pi xi dot, so I just replace the dot by a ket symbol. Okay, so it uh, so previously you can ask what is this brass symbol. So these symbols are not quantum bracket notations that I've used to make it to do the ease of transitions. So I just replace the dot by ket symbol. Now it is a quantum states. Okay, and this basically represents the overlap between two quantum systems. That is the main purpose of uh, quantum kernel, to finding the overlap between two quantum systems. Now you can say these are all mathematical terms. What is the physical realization of it? So let us understand how do we replicate in a quantum circuit. So a quantum feature map is generated through a variational quantum circuit. Okay, so you given inputs, you want to generate the phi x, so you'll have to go through a quantum that's called variational quantum circuit. So U phi x is the actual quantum circuit on 000 series of zero inputs. Okay, on okay, so these zeros are auxiliary qubits and x is the actual input feature here. So let us understand, this is called quantum state preparation circuit. Okay, so here I have used a single input qubit, that is the upper one that goes through the Hadamard gate, and the remaining qubits, that is I have used n number of qubits used as the auxiliary qubits to help the calculation. So I have passed these initial qubits to Hadamard gate to just generate the superposition principle of the qubit. Otherwise, it will not act as a qubit. It's simply a zero basis function. Okay. If someone says 0 or 1 basis is a qubit, no. Once we mix them, 0 and 1, with some coefficient, then it becomes a quantum state. Otherwise, it's the same as classical basis function with the notation of column vector, two-dimensional information instead of single in dimension information in classical. Okay, so I have used the Hadamard gate to give us equal superposition, and if you see closely, I have used two types of dot. One is a black dot and a white dot. So black dot suggests, we have just understood from the previous slides, black dot means if it is 1, it is enabled. Enabled means the lower block. Lower block is the target. Instead of single qubit, I can represent the entire block is enabled. And The moment it is 0, the second, that is u dagger. Okay, dagger symbol I've used. Okay, the Hermitian operation. Okay, I've used. Now you may ask, what is u phi? U phi x is a unitary gate operation. It may be series of gate operation, rotation gate, then cnot gate, like that. I'll also come to that. So to u phi x itself be a very similar quantum circuit. Okay. So initial states are all zero, n number of. So these initial states are auxiliary. There's not input. So input is only the above one. Okay. And here also we are measuring the same way, phi 1, phi 2, phi 3. And finally the final measurement is this. So let us understand how do you do that. So phi 1. So phi 1 is very simple. The first qubit is going through a Hadamard gate, so it will generate plus state, and plus state is 1 by root 2 0 plus 1. Remaining qubits has remained same. These auxiliary qubits are 0 0 0. After first Hadamard gate operation, in the below there is no operations. Next is, so Hadamard gate, you know that I have just explained. If we apply Hadamard gate on 0, you'll get 1 by root 2 0 1, that I have used here in phi 1. Next is phi 2. Now here is very interesting. So if phi xi says, if it is enabled, it will give you phi xi. Okay. Now I'm not going into that detail, that what is u phi xi. I will show you later on what is inside this black box u phi xi. So it says, if it is enabled, it will generate this phi xi map, feature map. It simply transform into your input features to. So u phi xi, definitely it is a rotation gate, cnot gate is there in between this. So if you can see, so if I go back again, the quantum circuit was 0 plus 1 into 0. So if we multiply just 0 0 0 to 0 and 1 0 0 0. So if control qubit is 0, there is no change. So that is the reason I kept it same. But the second part, the moment the control qubit becomes 1, I change the 0 0 0 to phi xi. So that is the role of this u phi x. Okay. Similarly, u phi 3x. Now, what I said, if the control qubit is 0, then the u dagger will be active. Okay. So this complementary operations we are doing. Now this 0 0 becomes u phi dagger x. Okay. And the previously we have already done this 1x. This is very simple operation. You just understand in cnot gate operations. Okay. So I can redefine it in terms of this. So whatever I have done, I have initialized some qubits 0 to the power n. Just read from the right, like the way we read. Okay, from not left. Then we applied a u phi x operation, then followed by u dagger x. Okay, and we are just measuring 0 out of this. Now we are last one the measuring. So last 0 to the power n is nothing but measuring these same zeros. Okay. So here you can see that this is the sequence of operations. First one, we have applied u phi x on 0, n zeros, and then we applied the resultant, that is S1, and this u dagger x, that is S2 on this. So basically this operation is called kernel. This is called a kernel trick in quantum support vector machine. So the significance of this line k xi xj equals to 0 to the power n s2. So we are trying to find out n zeros out of s2 quantum states. Okay, so we are measuring n zeros out of s2 quantum states. Okay, that means we are trying to find out probability of n zeros out of n2, and that is coming out as probability of 0 is. So this is some step jumps I made, some mathematical steps are there. So this is familiar with you because we have already got this state here, phi xj and phi xi. Okay, after phi 3. So I have reformulated here in this case. Okay, so this is the for linear kernel. For polynomial kernel, you'll have to make a perfect square of that. So you can generate a polynomial kernel to make, okay, with some power. Okay. So if you have n ancilla qubits mean auxiliary qubits. Okay. So you can generate like this way. So The upper one is the input qubit and remaining are the ancillary qubits. So you can also generate different ways. You see that we are applying series of, say here we have applied 2 times, okay, to generate the polynomial kernel. Last time I have replicated once, so to generate a linear kernel, so it is a polynomial kernel. So I have to replicate the same operation u5 and u dagger x twice. So this is simple. There's a jet feature map is already there in Qskit, so I can easily uh, generate it through the inbuilt function. Okay, though it is recently depreciated in Qskit. Okay, and so this is a, you can say, trivial look of whatever we are talking about u5 and u dagger x. So this is a simple uh, what I can say. Yes, u. So one u it looks like this. So there is a circuit which basically produces a feature maps. Okay, so this we have used a Pauli X gate and as well as Pauli Z gate along with the cnot gate operation. So this is very this is the main challenge. So design a suitable quantum circuit to generate those outputs. Okay, so these are all by intuition. Okay, so I have experimented. So I presented this work in one of the conference in Italy. Okay, so I have generated some synthetic data sets, and based on those data set, I have trained it. So as you see, as the training grows, so initially all these data points are overlapped each other, and training goes, it is uh, your data points are getting clustered. So I have used for binary classifications, very trivial kind of tasks. So here, in terms of visualization, if you can see, our main objective is to keep the data points in the two poles of the block sphere when we are representing in terms of quantum kernel. Okay, if you want to visualize, so and keep them apart so that there is less number of misclassifications. Okay, so so yes, so we have taken up to 100 epochs. Okay, yeah. Okay, so this is next is the very important, that is Verislan quantum linear solver. So this is basically uh, we use for solving any linear equations, and many large scale simulations are based on linear system as well as nonlinear system. Like one of the project I worked with in a startup, so that is our airfoil design optimization. Then card the design simulation software basically. So in design software like a car design, okay, so there are like millions of parameters to optimize. So you can optimize through a linear equations. Okay, so that give you a glimpse of that. So if you have, you know that any equation can be represented as ax equals to b system, set of linear systems. Okay, and here we are basically a uh, A is a matrix. Okay, so A is the actual approximated matrix. B is given, X is also given to you. You'll have to approximate A. Okay, so there is a way to do that. So I'm not going into that detail out of time. So we can uh, ge- generate through a Venezuelan quantum circuit, which is basically gives you the A. Okay, and on applying the input X on A, you can get the B. Okay, so I'm just skipping this part. These are these are BQLS algorithms. Okay. Okay, so now I'm moving. So how much time is left? I think 5 minutes, right? Okay. So I will not go into the details. So I'll just show you some of my, though it's not possible to make you understand or make the actual explanation of the research we are doing. So so that is one of the topic we explored at Purdue. So that is gate-based quantum neuromorphic computing. So that is a new direction in neuromorphic computing, because we believe that the biological nature of our brain is quantum. That is one of the Nobel laureate first predicted. That is, you might heard about Sir Roger Penrose. Okay, he first predicted the quantum nature of brain, and using those this characteristic, we can mimic many things in quantum circuit as well. So towards it, so I have started with the first very basic model of neuromorphic computing, that is spiking neural network. So in this case, we used a pre-trained classical spiking neural networks from an input image. So so here we used each and every pixels as a spikes. Okay, and and the length or amplitude of the spike is nothing but the image pixel intensities, and based on those spikes we generated some spiking activity, and those spiking signals are feeding to quantum circuit. Okay, so you can see that from the pretense. So now the question is why we cannot feed directly to quantum circuit. Okay, so yeah.
Just one second, the noise is coming. Kesar, some tarai. Uh,
Okay, uh, so in this case, so we have just reduced the dimension of the image. Even the image is 28 cross 28, and by reducing the way the image, even we have also reduced the number of classes to 4 class classification problem, because we have very limited quantum hardware setup, and we used a angle encoding. So angle encoding is basically, as you can see from the classical data, we encoded two three rotation gates. Okay, so though I have shown all same angles, but it's not same actually. So Hadamard, initially all the qubits, I'm not sure whether you can visualize or not. So these are all, initially all the qubits are zero state. Then we applied Hadamard gate to give a equal superposition or plus state. Then we have encoded the classical data to quantum through these rotation gates. So this is called angle encoding. So angle encoding is works like uh, uh, based on your input feature value. The higher the input feature value, higher the angles you have to you give or assign. So what we do, let's say if you have 5 different input features based on your input features value, let's say ranging from after normalization 0 to 1, and we divide into 5 equal parts, like each and every parts ranging from 0 to 0.2, 0.2 to 0.4, 0.6, like that. And we also divide the 2 pi angle into 5 equal parts. So if you have the input feature value classical data ranges from 0 to 0.2, you will also choose an angle between 0 to 35. Okay, so if you divide 2 pi angle into 5 parts, so each are having 35. Sorry, so what is the angle? If we divide 2 pi by 5 equal parts, let's say it's 35, 36 actually, 36. And so each sub interval is 36 degree, and if the your input feature value is ranges from 0 to 0.2, 0.2, 0.4, then which subinterval your classical data maps, and based on that you can choose any random value within that subinterval of angle. So if I give an example, if the input feature value is ranges from 0.2 to 0.4 range, then you can choose an angle 35 to 70 degree angle. You can choose any value randomly, because that precision is not possible. So, but due to this randomness, there is a lot of noise also incurred into the input. Okay, then followed by you have a set of input set of gates, that is cnot gate and rotation gate, and finally we measure the qubits, and then we pass through a classical optimizer. So there is no quantum optimizer available as of today. Okay, so this is post processing also classical. Okay, so we have used a spiking neural networks, and as I was telling that we have generated these spikes random in the sense there is no time there isn't time interval, there's no regular time interval, and mu1 mu2 mu3 are the spike amplitude, which totally depends on image pixel value. Okay, so each and every spikes are for a single pixel, and then summed up, and this is a leaky integrated pair model, which basically gives us the post spikes. So we have encoded this mu zero in a quantum circuit. Okay, so similarly random. So I'm not going to that. So I'll just show you some of the use cases. Okay, so this is a random spiking neural network. So it's all this Markov chain we have used. So we have studied for various number of gates, and you can see a lot of local minima. There is a Braden-Platius problem in this case. Okay, so their convergence is not smooth like classical due to slow convergence. Okay, so we have used various image data sets. Okay, and especially noisy data, because noisy data are handled very good at by using spiky neural networks. So that's the main motivation. And here we have checked the adversarial robustness. We have also implemented on the actual quantum hardware using IBM Quantum, but the accuracy is 0.616 the maximum accuracy you obtain on a quantum hardware. So this is primarily due to quantum gate noise and limited coherence time. Okay. Yes, but on the simulator, so this is not actual quantum. This simulator that is called quantum inspired, because we are using all these quantum gate operation and matrix operation on classical systems. So in that case, we obtain almost 90, above 90% accuracy. Okay, and we have checked with the adversarial robustness with increasing the noise levels, and we have also benchmarked with the classical models. So yeah, I have also worked with the one of the quantum library that is provided by NVIDIA to accelerate this Braden-Platius problem. So that you can see from the previous, you can tally previous convergence, it becomes better. Okay. Okay, so recently we also, since we only encoded the single variable mu naught, we also encoded the time variable along with the mu variable, that is a two-way encoding to give the real sense of spikes, because otherwise if you encode only in a quantum circuit, if you encode only amplitude, it will not access it doesn't behave like a spikes. So we have tried to give mm, both the encoding in a single quantum circuit. Mm. We have tested for very trigonometric use cases, not image is much tougher. Okay. Yeah, so tensor networks is another tools we use for as a quantum um inspired computing model for large scale simulation. So uh, mm, because you cannot simulate large quantum systems using quantum circuit, because that is most expensive operation, because of these two qubit cnot gate operations. So here I have given a try to reduce the complexity of the circuit, especially replace the cnot gate operation by tensor ring approximation. Okay, so this is a tensor ring approximation algorithm I have developed. Okay, and we have tested in on the various these standard benchmark datasets. Uh, okay, so this is a one of the use case of tensor networks, so that I have developed during my PhD for processing 3D data, 3D imaging data. So this neural network is a tensorized neural network. Okay, so on a Taka decomposition you might heard about. So this is a, yes, Taka decomposition we have used in these models. Okay. Yes, so quantum biometrics. So this is one of the very emerging technology that is for facial recognition. So one of the main problem in classical biometric is that, like if I give an example, this guy's face. So we are not able to detect using classical models or classic deep learning models. So we are giving how quantum can approximate better than the classical computing that we are giving a. We have come up with some quantum enhanced CNN model. Okay, that is multi-gate quantum CNN model to study this. Okay. So yes, I was talking about the. So this is the neural network I have developed. So the first I have given the mathematical form of a Qubits model in my PhD also. So this is I have also simulated up to 3 levels Qtreat on a binary classical systems. okay, by suppressing the upper level, so keeping the lower and middle levels. Yes, so the last one is my quantum regression. So as I talked about quantum classification problems, so one is this is the battery research. So this is basically, if I give an example, so to study the behavior of materials, it's not possible using classical computing to to report the total energy of the system by the interaction. So if I give an example, we can do only 30 elements because 30C2 number is a huge number. So instead of classical computing, the quantum is promising that is in many pharmacy and quantum chemistry. They are using the quantum regression. So I worked with one group in quantum physics when I was Germany. So materials for material design and simulations. So my main purpose is to show you some use cases where these quantum computing are using. And last not the least, this is the work we recently we do in we did in when I was in Purdue. So that is for Alzheimer disease. Uh, Sorry, I could not show you my work as Samsung that I am not allowed to do. Okay, so but yes, we are also doing various things how quantum can help us. Maybe on the proof of concept stage, how quantum can help us for better inferencing on the mobile devices. Basically, with all these AI technologies like generative AI. Okay, so that is our mainly we are also using tensorization techniques. Yes, so coming to this problem, so this is the one of the biotechnology research. Can are basically you might also aware of that US is already taken up this bio for quantum. Okay, uh, uh, this new quantum research direction is also established there. So we have taken the Alzheimer disease for the use cases, and we have studied the gene interaction in Alzheimer disease. Okay, this is a quantum gene regulator network. We have updated the network for Alzheimer disease. Okay, so this is all this we are using quantum entanglement in quantum regression. So we are taking the help of quantum entanglement. We can achieve better computational efficiency. Okay. Yes, so these are my funding agencies. So I am fortunate to have worked with various projects which are funded by all these leading agencies in the world in US, Germany, and India as well. Yeah. Okay, so these are some of my publications, and okay, thank you for your patience. So it's long lectures. Yeah.
Any question from the participant side? If there is any question, you may post into the YouTube chat or Google Meet chat. Sir, I have a just small query. I read it somewhere. Maybe you may think it's a very silly question. I read it somewhere that whatever have been developed theoretically till now through different funded research, theoretically whatever have been established, it will take at least 100 years to be implemented practically. At least 10%, 20% is also it will take 50 years to be developed and to come into the hand of common people through electronic gadgets what we use. So, I mean, what is your observation on it, sir? Is it how
Uh,
much theoretical and how much easy to implement actually?
I think you might have heard about the previous just one day before the NVIDIA CEO says that many people are expecting to 5 to 10 years, but he said that I think 30 years is underestimates. Like 30 underestimates means 30 years is a bigger time. 20 years we can see the all these things happen. But I think if you ask my so from my after talking to many people, I think within 5 years it will start giving the actual benefit in utility-based quantum computing era. Okay, so not in 150 years, 100 years, because this is one of the field which is growing the fastest. Okay, to the emerging technology. So, like if you count the number of qubits come up with by IBM Quantum, they are doubling each and every year. Okay, and also Google is also recently come up with the logical qubits idea. so that can get rid of the errors or noise. Okay, yeah. So 50, 100 years is, I think, it is. Yes,
So
it is
maybe
for
just
average.
someone's idea. Okay, okay. Thank you,
Yeah,
thank you.
yeah.
Any other question from any participant or no? No, not till now. Okay, sir. On behalf of everyone here, I would like to extend my sincere gratitude to Dr. Debanjan Kumar Debanjan sir for sharing such valuable insights with us today. Your expertise, knowledge, and engaging presentation have certainly enriched our understanding, and we are truly thankful for the time and effort you have put in this session. Sir, we are sure that the lessons learned today will have a lasting impact on all of us. Thank you once again on behalf of all the participants and the organizing committee. Now, as a guest of honor, we are presenting a certificate which is displayed on the screen, and we will be happy if you accept it. Yes, sir.
Thank you very much.
Uh, okay, sir. And really, we are honored that you joined our LTP. Thank you, sir. Thank you very much.
Thank you, everyone.
Thank you. And dear participants, our next session will be started tomorrow at 10 a.m. sharp.